All right, everybody, welcome. This is Mr. Valconi coming to you live. If you like this video, be sure to leave a like and subscribe. Yeah, don't be afraid to share. I'm looking for that million likes and million subscribers. So yeah, just help me get there. I appreciate that, friends. Thank you. This is section 12.1, so we're going to be looking at a little bit of using electricity in the home and how much that kind of stuff costs. So we're going to be starting with direct current and alternating current. And yesterday, somebody even asked me, sir, what's the difference? What's this DC? What's this AC? And today we're going to get into that. So right now, you should have your notes open to section 12.1 and section 12.2, which are on the same page. And just to the teacher in the room, if you could just pause the video to give the students time to copy down the note and make sure everybody's on pace, that would be great, just because I will be moving kind of fast through this. So just pause whenever you need to make sure everybody's caught up. Okay, so let's take a look at direct current. So direct current is also known as DC. So direct current is current that travels in one direction. So we have current traveling in a single direction, and this is what you are used to in like pretty much every circuit we've ever looked at. So in our circuits, what we've been doing is we've been drawing these circuits wicked, and then I always made you label the positive and the negative, and then I had you draw this like letter I. So I made you draw this little arrow and then this I symbol. And what that shows you is that's the direction that current is traveling in this circuit. And at no point does current ever like start jetting it this way and then just be like, yo, no, I'm not feeling it and I'm heading back home. It does not do that. Current always, always, always travels in one direction, which was also an excellent band. So current needs to remain consistent in one direction. Most of our circuits that we will be dealing with are that way. So the applications of this, these are in some of our small electrical devices. So pretty much anything battery powered would be a good example of something that uses DC current. So it's current that travels in one direction. A good example of that might be your cell phone or a flashlight. Either of those two things would definitely be using DC current. But there is a gigantic problem, because all of the electricity that comes out of the walls, like the stuff you use to charge your iPhone, is totally not DC. Remember, DC normally comes from batteries, so let's write that in. Normally comes from batteries. Okay, so we have this direct current that normally comes from batteries, and if you've noticed, you probably don't use batteries to charge your phone anymore. You plug them into the wall. And the unfortunate part for us is the wall does not supply direct current, it supplies alternating current. So we're going to come back to this question here, why must we use an AC adapter, in just a sec. And first we're going to talk about alternating current. Alternating current is current that switches directions. Periodically. So this current goes back and forth, back and forth, back and forth really, really, really quick. And by really, really quick, I mean like so lightning Usain Bolt fast that it's absolutely ridiculous. So let's take a look at our circuit again. So if we have our circuit, here's our circuit. Great, we've been used to current going around and around and around, but here what's going to happen is electrons are going to move back and forth like super, super fast, basically just in one spot. And now you're thinking, okay, but if electrons aren't really moving around, how are they transmitting energy? And it's a really good question, but it's actually got a simple answer. And the easiest way to think about it is if you think about a saw. When you have a saw and you're cutting down like a gigantic tree, what you do is you're moving that saw back and forth, back and forth, back and forth, but the blades of the saw actually aren't going anywhere. They're staying relatively the same in one spot. So that's a good way of thinking about alternating current and how it impacts our electricity. You will not be studying anything about alternating current other than the definition and kind of how we go from AC to DC in this course. And truthfully, you probably won't be touching on alternating current until university if you decide to pursue physics in that capacity. So the applications of alternating current, this is the stuff that comes out of our walls. It's the stuff that's really high power. This would be like our large appliances. So stuff like our fridges or our stove. Okay, good stuff. So pretty much all of our big appliances are going to take the role of alternating current. So now we go back to this question, why do we use an AC adapter to charge these devices at home? And that is a good question. It's because we need to change from AC to DC. So the electricity coming out of our walls is AC, and the electricity that's needed by our phone is DC. So because of that, we need to actually make the switch from AC into DC. So we actually have a special device that is used to accomplish that. That is called a transformer. Awesome. So I would keep that definition in mind. A transformer is what we use to switch from AC to DC. Remember, our walls supply AC. We need DC in things like our phones or other small appliances. So now you're probably thinking, okay, well, if most of the stuff we use uses DC anyway, why would we have AC in the first place? And this is actually like one of the coolest things in electricity, and I'll probably tell you a little bit more about it when I come back. But we use AC in our homes because DC loses energy over long distances. So DC is actually terrible at being transmitted over anything other than a couple of feet. So if we're trying to get it like from here to Niagara Falls, by the time that like 100 volts of DC energy gets sent from Niagara Falls to us, it might be like 2 or 3 volts. AC is probably still going to have like a 99% intact ratio, so it's still going to be looking great, but DC is going to be the big problem there. So we use AC because it's much better at being transmitted over very long distances. And really, these two definitions are pretty much all you're going to need to know for section 12.1. So with that, let's go to section 12.2. 12.2 is all about power, and here we're going to be using a lot of formulas to help us out. So 12.2, we're going to start with electrical power. Power is the rate at which energy is used. So if you've heard of someone being very, very powerful, it just means that they're using a lot of energy very, very quickly. And in electricity, it's the exact same thing. It's how quick are we using up our electrical energy. The units for power, these things are measured in watts. And we have a symbol for it, W. Lots of times, though, things are like way more than 1,000 watts. So many times, we convert things into kilowatts, just because they're a little bit bigger. To go from watts to kilowatts, which is what we're going to be doing a lot of the time, when you do that, you want to divide by 1,000. So you should be able to try that with these two things down here. We're going to go from 1800 watts to kilowatts. So just give you a second and try that. Okay, so you should have been able to divide that by 1,000 and get 1.8 kilowatts, and if you divide that by 1,000, you should have got 0.2 kilowatts. Okay. Whenever we are talking about power, that's normally represented by the symbol P, so an uppercase P for power. Now, it's really difficult to talk about power without talking about energy, because remember, power is just how fast do we use up our energy. So energy is measured in joules, Joules, and we use a J for it. But we actually don't measure a lot of our things in joules because joules are just way too small. So what we do instead is we convert those things into a special unit called kilowatt hours. This is measured in kWh, so that's the symbol for kilowatt hours, kWh. And this is the one you will be using much more. Okay, next thing we want to talk about is this guy over here. These are called Energuide labels, and basically they just tell you a quick summary of how much energy a device uses on average in a year. Okay, so this is a really good thing for consumers because when they take a look at this, they can see how much energy is my fridge or my stove or my oven using. So that's where you're going to find a lot of these things. So for example, your fridge or your stove or pretty much any large appliance is going to have this. Okay, now we're going to get into our formula. So it is time to do this. We have a formula that we're going to take a look at here. So the formula is cost equals power times time times price. So this is one of our formulas, but it's very, very specific. So we have to make sure that all of the things in this formula are in very specific units. So our power, these things need to be in kilowatts. So remember, that's when we took our watts, we divided by 1,000, and we ended up in kilowatts. Our time always need to be in hours. So if I give it to you in minutes, you need to figure out how many hours is 120 minutes. You'd be able to change it into 2 hours and then use it in the formula. And then our price. So our price is either going to be in dollars or cents. It doesn't matter. So if I give you the price in dollars, just know that your final answer is obviously going to be in dollars. If I give you your price in cents, know that your final answer is going to be in cents. Good. So that's one formula that we have. But sometimes I won't give you the power or the time. Sometimes I'll just give you the energy instead. So the other formula that we can use for this. Sometimes we're going to look at energy equals power times time. Okay. Great. So if we're looking at those two things, these things are going to be very, very helpful for us. So let's take a look at our first example. We're going to list what we have. So the very first thing we have is a hairdryer. This hairdryer, it says it's rated at 1200 watts. So you have to be able to take a look at this and figure out, okay, 1200 watts, like what does that mean? Is it power? Is it time? Is it price? What is it? So we know that watts corresponds to power. So our power is going to be 1200 watts. But that should already be raising some alarm bells because what did I just say? I said power always needs to be in kilowatts. So before we do anything, we need to convert those watts into kilowatts. And how do we do that? We, of course, divide by 1,000. So 1,200 divided by 1,000 is going to give you, oh my God, what is this? What's going on over here? 1.2 kilowatts. Okay. Next thing it says it's used for 10 minutes each school day. Okay. So now it looks like we're talking about time. So we're talking about minutes. So our time is 10 minutes. But it's more than that, right? It says it's each school day. So how many days do you go to school? Well, for most of you, it should be 5 days a week, although that's probably not true. But yeah, it should be 5 days a week. So we're going to go 10 minutes every school day, so times 5. So that means every week we're using it for 50 minutes because we're using it 10 minutes a day. But then it says we're using it on all 5 school days, which is perfect. So we got 10 minutes times 5. So right now we're at 50 minutes. Excellent. But our time should be in hours. If it's not in hours, we need to figure out a way to get it there. So how do we get it there? Well, if you're ever in minutes, how many minutes in an hour? There's 60 minutes in an hour. So we just need to divide by 60 minutes. 50 minutes divided by 60 minutes, that's going to give me 0.833 hours. Excellent. From here, the last thing we're given is our price. So it says when the cost of electrical energy is 8.8 cents. So that's the last variable we're given. So our price is 8.8 cents. We have everything we need. We can use our formula. So cost equals power times time times price. And now we can just start substituting everything in. So our cost is going to equal our power, which is 1.2. Our time, which we calculate to be 0.833, times our price, which is 8.8. So when you do the math on your calculator, you should get a value pretty close to $8.79. Now, you need to figure out what units am I talking about here. Well, you have to, for that, look up here. I gave this to you in cents, which means your final answer should be in cents. But I've never heard of anybody getting 8.8 cents change, so we need to round that. So we're going to actually round that up to 9 cents as our final answer there. Awesome. That looks lovely. Okay, we're getting there, folks. Last formula we're going to be taking a look at is efficiency. So efficiency is just how much energy do we waste. So we want things to be as efficient as possible. So like those old school light bulbs, those things were super inefficient. So they had an efficiency of about 5%, which means that for every like 100 units of energy, we're only getting out 5 units of light. So we were wasting a lot of energy doing that. So we don't want that. So we're looking for devices that are extremely efficient. So we started using fluorescent light bulbs, and those things are about 20% efficient. So that means if we have 100 units of energy that we're putting in, we're actually getting 20 units of light out, which isn't bad. So we have a formula for that. Efficiency is going to equal P out over P in times 100%. Or sometimes I'm not going to give you power, I might give you energy. And for energy, it's going to be efficiency equals E out over E in. So these things are always going to be percentages, so you have to make sure that you're multiplying by 100% when all is said and done. I'm going to give you a tip. If you do your math and your efficiency is over 100%, you have an issue. So your efficiency should always be lower than 100%. If it's not, you need to redo your problem because you have screwed something up. Okay. Efficiency should be lower than 100%. Additional tip. Your smaller number should be on the top. All right? Using that, we should have no problems doing this. Okay, so let's take a look at this question that we're given here. It says an AC adapter operates at 28.6 and the output is 1.04. What is our efficiency? So as soon as you see that efficiency formula, we know we're going to have to use, or sorry, that efficiency word, we're going to have to use one of our efficiency formulas. Now the question is, which one do we use? Well, we're given everything in watts, which means we're going to have to use our efficiency with our power. So we're going to use efficiency equals P out over P in times 100%. So we just need to figure out what is our P out and what is our P in. So let's try to figure that out. Our P out, it says our output is 1.04, our output. So that's going to be our P out, 1.04 watts. Our P in is going to be 28.6. Here in the blue, I said your smaller number should be on the top. That's always going to be your output. Your output will always be smaller than your input. If you can remember that, you're going to be in great shape here. So you remember your output is always supposed to be smaller than your input. So when I do this efficiency problem, P out divided by P in, I have 1.04 divided by 28.6 times 100%. So get out your calculators and do that. When I did it, I got 0.03636 times 100%. So if I multiply that by 100%, I would get 3.636%. Now you need to do a check. Does this make sense? Well, is it lower than 100%? Definitely is. So yeah, we're good. 3.636. It's not very efficient, but it is the correct answer. Okay. Now, today, what you're going to be working on is this worksheet. So you're going to be working on this today, and hopefully you get it done today and tomorrow, and that way we can kind of take a look at it when I get back. So the very first thing you need to do, we're going to be looking at how much does it cost basically to run your house. So all of these wattages, they need to get changed from watts into kilowatts, and by now you should have a good idea, okay, how do I do that? To go from this to that, you're always going to be dividing by 1,000. So if we're dividing by 1,000, we should be able to do that with all of our numbers. So 600 divided by 1,000, that'd be 0.6 kilowatts. 500 divided by 1,000 would be 0.5 kilowatts. And you can go ahead and finish that chart. These numbers are going to be very important because we're going to have to use those to fill in our table on the back. So let's take a look at what I mean by that. So when we flip over our page, here we go. So now what we need to do is we need to figure out how much do these things cost to use. Before we even get started, I want you to write something in. Remember, energy. What is energy? So energy equals power times time. All right? And if we want cost, we can use our formula, cost equals, oh, that's going to be way too big. This is going to be energy times price. So we just need to take the price, which is, guess what, given to you right here. Our price is always going to be 12 cents. And the energy is what we're going to be figuring out in the column before. What's up, Gina? Your phone? I don't know. I don't see it. Do you want me to call it? Are you sure? Hi, everybody. Say hi to Miss Kavanaugh. Miss, they definitely would have said hi. All right. Power. We're always going to make sure that it's in kilowatts. So if we take a look at our next line, I'll do one with you here. Our clothes washer. What is the kilowatts of that device? Well, to figure that out, we just need to go back to the page we just did. So if you look at our clothes washer is right here. It says 600, and we converted that into kilowatts, so 0.6. So under clothes washer here, we're going to put 0.6 because that's what we had on the page before. Now, how long was it running for? Well, it looks like it was running from 7:30 till 10 o'clock. So 7:30 till 10 o'clock is 2.5 hours, so 2.5 hours. So how much energy did that use? Well, that's a good question. And how do we get it? We take our power, which is 2.5, is 0.6, and we multiply it by our time, which is 2.5. So if you took your calculator, 0.6 times 2.5, that's going to give me 1.5 kilowatt hours. From there, we can take our energy and multiply it by our price. And remember, our price is always going to be 0.12. So we're going to take that 1.5, multiply it by 0.12, and we're going to get $0.18 because, remember, it's given to you in dollars. Awesome. Awesome possum. All right, let's do one more. Let's do, Okay, let's do Saturday's video game sesh. All right, so this person was just straight up ripping Fortnite for probably far too long. Let's take a look at how much this video game console uses. So the video game console is 250, so we can convert that into kilowatts, so 0.25. And that's an important number to remember because that 250 to 0.25 we can now put into our table. That's our video game console number. So whenever we see a video game console, we know that it uses 0.25. So we could just, every time we see video game console, like up here, we could fill that in as 0.25, and every other time, exact same time. The thing that's going to change is how long did we play for? So we played from 12:30 to 5 o'clock. That's disgusting. That's way too long. So that's 4.5 hours and no solo wins. So 4.5 times 0.25. So now we have our power, 0.25. We have our time, 4.5, So to get our energy, if you take a look at the top of your page, you should have written down the formula. Energy equals power times time. So we take our power times our time, and 4.5 times 0.25 is going to give you 1.125. Great. Once we have the energy we use, now we can multiply it by our price, which is always going to be, for this question, 0.12. That ends up being 0.135. Okay? This table should not take you overly long to complete. And you're going to start this today, and then tomorrow you're going to start reviewing for your test. So we're going to move from this. Once you're done that, there are some very, very good questions. One thing I'd like you to do, though, is for 1B, could you please just cross out this, because I actually do not want you to do this question. It's probably a little bit too difficult right now. But everything else you should be able to do, and the rest of them are very important. So I did all of these for you. All the solutions are up there. So please make sure you do them. Do your work hard, and check your solutions online, because this is going to be a very, very important part of your test. Whenever I get back, which will be Monday, we will take up whatever questions you have. Okay? Any questions? I don't hear anything, so good. All right. How do I spell that?